Hey everyone, if you've ever been in the lab, spent ages building a series circuit, you plug it in and absolutely nothing happens, well, you know that sinking feeling all too well. Today, we're going to turn that frustration into a superpower. We're going on a fault-finding mission, and by the end, you'll be a regular circuit detective. So let's get started.
So, there you are, staring at your completely dead circuit. The power supply is on, everything looks right, but there's just no sign of life. It's a classic problem. So what's your first move? Do you just start pulling components out at random and hoping for the best? No way. We need a strategy. We need a logical process to hunt down whatever's gone wrong.
You know, in any series circuit, there are really two main culprits we're looking for when things go completely wrong. Over here on the left, you see a happy, healthy circuit. It's got a complete, unbroken path, and that means current can flow. But look at the one on the right. See how the path is broken? We call that an open. The other possibility is a short, which is when the current finds an unintended shortcut. These two guys, opens and shorts, are what we're hunting for today.
First up, let's go on the hunt for the open circuit. This is usually the prime suspect when your circuit seems completely dead, with zero current flowing anywhere.
So what is an open, exactly?
Well, think of it like a drawbridge that's stuck in the up position right in the middle of a highway. It's a complete break somewhere in the current's path. It could be a resistor that's burned out, a wire that's snapped, maybe even just a bad connection on a breadboard. But here's the crucial takeaway. Because that path is incomplete, the total current in the entire series circuit immediately drops to zero.
And here is a perfect example. See the multimeter? It's set to measure current in amps, and it's reading a big ol' 0. And why is that? Because inside one of those lamps, the little tiny filament has broken. That tiny break is our open. And it doesn't matter how perfect the rest of the components are. In a series circuit, if there is a single break anywhere, the whole party stops. No current can flow.
Okay, now this is really interesting, and it's the single biggest clue you'll ever get for finding an open circuit. Take a close look. Since there's zero current flowing, Ohm's law tells us that there's going to be zero voltage drop across all the good components. So where did the source voltage go? Well, as you can see in the diagram, the entire source voltage appears across the break itself. The full 10 volts from the power supply is being measured right across that open resistor, R4. That, right there, is our smoking gun.
So we know what to look for, but testing every single component one by one, especially in a big circuit, is just not efficient. A much smarter way to do this is called the half-splitting method. It's basically a divide-and-conquer strategy. You measure the voltage across half the circuit, and based on that one single reading, you can immediately rule out half of your components. It's brilliant.
Let's walk through it together. So our first move is to put our voltmeter probes across the first half of the circuit, covering both R1 and R2. And what do we read? 0 volts. Now, this is actually fantastic news. It tells us that this entire section is perfectly fine, because remember, if the break were in here, we'd be reading the full source voltage. So in just one measurement, we've cleared half the circuit. So, since we know the first half is good, we just move the meter over to the other half, across R3 and R4. And, would you look at that? Our meter reads 10 volts, the full source voltage. That is the confirmation we were looking for. The break has to be in this section. We've just narrowed our search down from 4 possible components to only 2.
Now for the final step. We just have to check the last two suspects. So let's measure just across R3, and we get 10 volts again. Bingo! We found our culprit. R3 is the open component. You see? Just a few logical steps, and the case is solved.
All right, so we've totally mastered finding opens. But what about that other troublemaker? Let's switch gears and pivot our investigation to learn how to expose a short circuit.
A short circuit is pretty much the exact opposite of an open. Instead of a break in the path, it's an unwanted connection. You can think of it as a secret shortcut that the current discovers. And because current is, well, lazy, it will always take the path of least resistance. So it'll completely bypass the component it's supposed to go through and take this new, super easy path instead. And trust me, this isn't just some textbook theory. Shorts happen in the real world all the time. A little stray blob of solder can accidentally bridge 2 tracks on a circuit board. A tiny wire clipping could fall and connect 2 points that should never touch. Even just the leads of 2 components accidentally touching can create a short. These little physical mistakes can have some really big consequences. And the biggest consequence of all is a huge surge in current. Just look at this example. Before the short, the circuit is chugging along with 1 amp of current.
But as soon as that 33 ohm resistor gets shorted out, the total resistance of the circuit drops way down. And the result? The current jumps up to a dangerous 3.57 amps. All that extra current generates a ton of heat, and that's what can damage your other components or even fry your power supply.
So how do we find it? Well, just like with an open, there's one critical clue we need to look for. Since all the current is bypassing the component through a path that has almost zero resistance, there will be, you guessed it, basically zero voltage drop across that shorted component. If you put your meter across a component and read 0 volts when you know there should be a voltage, you've probably just found your short.
And guess what? We can use our half-splitting technique here too. So let's say we know a short exists because our total current is way higher than it should be. Now, in a perfectly working circuit, we'd expect to see 5 volts across this first half. Instead, we're measuring 6.67 volts. So why is it higher? Well, because a short somewhere else in the circuit has lowered the total resistance, which makes the total current go up. This bigger current causes a larger voltage drop across this good section. So a higher than normal reading here tells us this part of the circuit is actually okay.
Okay, now we measure the second half, across R3 and R4. We'd expect to see 5 volts here too, but our meter's only reading 3.33 volts. This incorrect, lower than normal reading is our big clue. It tells us the short circuit must be hiding in this half of the circuit, because that short is dragging down the combined resistance of this particular section.
Time to isolate the problem. We measure across R3, and we get 3.33 volts. Well, that's not 0, so R3 is fine. That only leaves one suspect left. By process of elimination, the short has to be across R4. And if we were to actually put our probes across it, we'd see exactly what we expected, 0 volts. And just like that, another case is closed.
Okay, theory's great, but let's see how all this plays out in a more practical, real-world application. We're going to diagnose a fault on an actual voltage divider circuit board.
And here's our patient for today, a standard voltage divider. Its whole job in life is to take one 12-volt supply and chop it up into several different, smaller voltages at each of these pins. The problem is, it's not working right. And luckily for us, we've got the measurements to prove it.
And here is our evidence, the case file if you will. This table compares the voltages we should be getting at each pin with what we actually measured. Take a good look at the data. Our mission now is to use these clues, these differences between what's expected and what's measured, to find the exact location of the fault.
So let's work through the logic on one of these classic fault scenarios. Let's say you take your measurements and you find that pin 3 reads 12 volts and pin 4 also reads 12 volts, but every pin after that reads 0. What does that tell us? Well, R4, R5, and R6 are all supposed to be drawing current. The fact that the pins connected to them are all at 0 means no current is flowing through them at all. So why would pin 4 be at the full 12 volts? It all points to one thing: an open circuit on the connection right between pin 4 and resistor R4.
We've covered a ton of ground here, so let's take everything we've learned and put it all together into a simple but really powerful toolkit that you can take with you to the lab.
This slide right here is your ultimate cheat sheet. For an open circuit, just remember these 3 things. The current drops to 0, the resistance at the break is basically infinite, and the full source voltage appears right across that break. And for a short circuit, the current is way higher than normal, the resistance across the short is almost 0, and the voltage across that short is also 0. These characteristics are the fundamental clues for pretty much every troubleshooting job.
So you are now officially equipped to find a single open or a single short in a series circuit. But here's a little something to chew on as you move on to more complex stuff. What would the symptoms look like if a circuit had both an open and a short at the same time? How would those clues we just talked about combine or even contradict each other? That, my friends, is the next level of your detective work.